Hello. I don't know how to start this because we've been talking for the last 10 minutes. My name is David Lovett. I run a small YouTube channel. If you don't know, I run a small YouTube channel called Usagi Electric. And I think the reason that they chose to put me in this seat is because very recently I decided to try and build a homebrew computer. And I love homebrews. There's a lot of homebrews out in the world. And not always, but they often use known chips like the 6502 or the Z80, which are relatively easy to build a homebrew around. Grant Cyril, I don't know how you say his last name. Cyril. He's got a funny last name, but he's got a wonderful design of how to build like a 7-chip Z80 homebrew and a 7-chip 6502 homebrew, which are like very minimal single board type stuff. And I was like, that's really cool. I would love to build a homebrew, but you know, I like hard mode. So I was like, I'm going to build a homebrew out of the TMS9900. I think it's a beautiful chip. I think it has some really interesting architectural designs. Interesting used in every sense of the word. And so Jay reached out to me and said, hey, we've got somebody really special here, Dr. Granville Ott, who was actually involved with this chip and with TI in some way. So, Dr. Ott, would you mind telling the people why you're sitting in this chair?
Well, I was the chief architect for the TI home computer. I was actually a professor at the University of Missouri, and I wanted to take a sabbatical. And I stopped by to see my old boss from the seismic days when we worked on seismic computers in Houston. And he said, oh, I really need somebody because I want to build a home computer that goes into the home, not just a computer for the hobbyists. And the guy I was going to use and did my hardware design stuff expert died. And I really desperately need somebody. Can you it's at least do your sabbatical here. And I did, and stayed. I decided after I got into the thing to go ahead and buy a house in Dallas. And a month later, they moved everybody to Lubbock. So I bought a house in Lubbock. I still have the house in Missouri, so I had a house in Missouri, a house in Dallas, and a house in Lubbock. But that's a different story and hadn't got anything to do with the computers. But that's just how I got into it all. And to build a home computer, we were working on what to use. And so that got into that TI likes you to use TI products within what you're doing. Whether it totally fits or whether it's perfect or whether it's optimal, doesn't really matter. If you can use a TI product, you're doing the right thing, see? So they really decided that we ought to be using the 9900 CPU because TI had a 990 computer that they made out of Austin. And let me go back just a little further. The mini computers that TI made, I had designed the 980 when I was in Houston before I left to teach, and so they had that as one product, and then they had the 960, which was modeled from Dallas, which then got reduced to the 990 because the 960 was a much bigger machine. They needed a really small machine for a reservation machine for motels and stuff, and so they cut it down. And the nice thing about the 99 architecture was that it can be minimized in cost. And going back one step further, it came from a flight control computer that the military computer group in Dallas built for, I guess they put it in the F-16 and also in the the F-22. They had the flight control computer, different companies had different parts of the machine, but the flight control computer they had designed a special computer which had a lot of flexibility, a lot of input and output of all the little things you needed to do. And they ended up creating the architecture that the 990 had. And that was a 32-bit computer there. And since they were making the 16-bit mini computers, they figured out how to cut that down to a 16-bit computer. And so they had 3 different architectures, and that was tearing them up on software, because if you can't sell a computer without some software, and having 3 totally different architectures was disastrous. So they sent somebody from down from Dallas that was into software, and he said, we'll just pick one direction and we'll let the others just, the semiconductor used them as a control computer, the 980, because they were already using them from Houston from nearly a decade earlier. So the 990 was there as their architecture, and they needed a nice low-cost version. And one of the engineers that used to work for me in Houston took the thing and cut it down. It was for a motel reservation system, and they wanted to minimize the cost. And you can make it pretty low cost. Now, the 990 has some features that make it really flexible to use. The registers, you have a whole section of memory that's defined as I/O registers. And so you can have as much as I/O as you want, which was great for the flight control computer, and is great for a lot of applications, but it keeps you from having as much hardware, so that you can have a pretty limited system. So the reservation system worked really nice. So that's kind of how that all architecture ended up coming together. And then when we were going to build the home computer, we thought we would get the 6502, which is the cheapest, fastest little thing on the market, which came out in the Apple. And of course, management said, oh no, wait a minute, you got to use a TI computer. And so after a little bit of consternation, we figured out we had an 8-bit home computer system, and we had a 16-bit architecture, and we had to cut it down and play with it a little bit. But that's how that all kind of flowed together. And so that's kind of the background of all of this. And then we got to the point where, there's a 9900. Now, I didn't personally do or was not involved in architecture or the software or all of the other stuff that's important to all of you who want to use a 9900. I was primarily trying to figure out how to make hardware work with whatever we had to use. And so I'm not as proficient in all of the neat features of the thing, other than noticing that it takes 4 clock cycles to do anything. To make a cheap, computer that doesn't have much hardware in the computer itself is great, but that slows it down by a factor of 4, which isn't bad unless you need speed. And initially, we didn't need speed for the home computer until some of the programmers wrote a really hot game like Parsec. And all of a sudden, everybody wanted, a hot game, and you're trying to suck all the speed you can out of it, and that's when you wished it ran 4 times as fast. And that's kind of the viewpoint from where I was coming from.
Okay, so you started with the 980 in Houston, correct?
Right.
So the 980 and the 990, and I think the TI naming scheme is very confusing, if we're being honest here, because you guys use 9 and then some number, and it's used everywhere. So the 980 was a mini computer that you were the lead architect on, but it has absolutely nothing to do with the 990,
That's right.
architecture-wise or design-wise.
That's right, exactly.
They're completely separate.
Totally separate.
Because that makes sense, right?
And the only thing that really happened is the 990 came down from Dallas with the military computer people that came down with it. And the 980 came from Houston with the people that, some of the engineers that worked for me were transferred. They took that whole group in Houston and moved them to Austin to make Austin the computer center for mini-computers. And they ended up going 3 ways simultaneously, which turned out to be, not really great, but you drown in the lack of, or you strangle because you don't have enough software. And so computers are great, but if you don't have enough software to go with it, you die of thirst.
Was there a little bit of competition going on between you and the 980 team with the 990 team to see who could kind of come out on top? Internal competition, shall we say?
From a 980, the 980 I designed in 1967.
Okay.
67 to 68 as a special product to go to semiconductor because they didn't want to continue using the 24-bit machine that I had designed a year earlier. And so the 980 was designed specifically for a semiconductor to use in their test equipment. The transistor lines testing, they wanted to have it all automated with the computer. And so we had initially built a 24-bit machine, which was in a big cabinet, and it had bit slice things. And of course, technology was moving so fast. We built it with 73 series logic, which was in gold-plated flat packs, ceramic flat packs. And the next year, they came out with the 74 series stuff and obsoleted all of that almost immediately. And so then we did the 980 using the 74 series chips. And as far as I know, they may still be using some of those 980 computers. They were just like a normal mini computer size. Once you got a good computer controlling your equipment, you don't need to change it until you completely change equipment.
So it's interesting that you mentioned because I've never heard of 7300 series stuff. But the 7400 series stuff is like ubiquitous and everywhere, and we use it. So presumably the early 990 machines were also all 7400 series chips.
Right.
Correct. And so the CPU initially on the 990 machines were built from discrete 7400 logic built up.
That's right.
Essentially one gate at a time.
Right, yeah. And you had some pretty good gates. You had a dual full adder was one of the key chips you used to make your CPU out of it. You just had, for a 16-bit machine, you had put 8 of those chips in, and there was your ALU.
Yeah.
And so that was, semiconductor was making more and more complicated chips. Like if you use something this year, next year, there was a chip that had twice as much stuff on it at least. And so it was, like you're on a treadmill and they kept turning the speed up.
Which ultimately led into something like the 74181, which is the 4-bit bit slice ALU.
Right, exactly.
Which is used in, actually, my Data General Nova out there. I've got the Data General Nova 1210, which makes use of a 74181. And so presumably as the 990 progressed through its evolution, the CPU got smaller and smaller, using larger and larger integration onto the chips.
And see, I kind of disconnected from all of that in 68 when I left to teach up at the University of Missouri.
Okay.
And so that's kind of a blank spot. I can't tell you what was going on in that whole 8 years before I took a sabbatical.
Okay.
And then I came back, and when I came back, I got plugged into the need for some of the new products, and we were looking at various ones. I was at the first meeting that was looking at the possibility of doing the Speak and Spell, and I got to do the home computer instead of the Speak and Spell because that was one of the reasons why I was left Missouri to, when I was on sabbatical. But we were looking at that. We were also looking at a new TV tuner just for to be off to the side. But the TI had developed a SAW technology, surface acoustic wave, and those chips could make a fantastic TV tuner so that you could separate all of the stations instead of just 4 and 5, the ones that had a little bit of frequency between the channels. With the SAW filters, you could actually separate and introduce, put them closer together. It used to be you'd see 4 and 5 in the same town, but you would never see 6 and 7 in the same town because they were too close together and they would interfere with each other. Anyway, the SAW filter ended up being, the TV manufacturers had a fixed price, and it was 20 to 30% too expensive, and so they wouldn't buy it, the tuner with SAW filters.
Now, you mentioned the Speak and Spell before we get into the TMS9900 here. The Speak and Spell, and I believe uses the same microcontroller as pretty much the entire calculator lineup, which is going to be the TMS1000 series.
That's right, yeah.
Did you ever have a chance to actually work with the TMS1000 series of chips?
Not really, no. I was just kind of looking at it from the side. I did do some stuff with the Speak and Spell. The Speak and Spell, once they got it designed, they had one engineer that took that as his personal goal, is to do that one chip, and he would be designing it at night while he was laundering his baby's clothing in the laundromat in Lovett. Anyway, Larry Branningham, some of you may have, I'm sure know of him. Anyway, he had taken that and run with it, and it wasn't fast enough. The hardware just wouldn't run at real time, and so I showed him how to make a pipeline multiplier, because I did that for the seismic computers in Houston. The seismic computers, I sped them up to the point that a sign in the museum in England, I was going through the museum with my kids when we were young, and we went to the geophysical area of the British Museum, and they had a big sign and a picture of my computer, and it listed it as, it said, the fastest commercial computer in the world. That was back when I was doing seismic computers. Anyway, that is where I was coming from. Then I came back, and my same boss that was from Houston had joined the calculator group, because Shepard, actually, I don't know whether it was Busey or Haggerty, had wanted TI to have a scientific calculator. Here was HP with their scientific calculators, and TI had all of the non-scientific calculators, and kind of each one owned that segment of the business, but they wanted a scientific calculator, so they hired my Houston old boss to come back to TI and do a scientific calculator. And he did the 52 and then the 59, and then he was ready to say, hey, we got enough smarts going into little systems that we could build a computer to go into the home. And so that's right when I showed up, and the home computer, we presented it to management, and they said no, and they gave us some guidance, and then we went back and they said no, and we went back a third time, because they said, we don't want this thing to be a game. TI wants a good professional image, and you can build product goes into the home, and it can play games, that's great, but we don't want it to be just a game. And so they took, let's say, 3 passes before they approved doing the home computer. And that's kind of where it all came from. And then when we were going to design it to meet the cost goal, a nice, fast 8-bit computer was perfect. And they said, no, TI makes their own computers. You can use the TI computer. but nobody was buying those. TI built the 9900 because they wanted to have a computer chip. When I did the 980 24-bit machine, they came down to see whether they could make a 1 or 2 chip computer out of it. And it just was too complex. We had 8 CPU boards in it. And so finally, the 990 architecture was small enough that you could squeeze it on a chip. And so that's when they launched the development of the 9900.
Which was essentially a large-scale integration of the discrete CPU that was in the 990, correct?
Right, exactly.
So this is very similar to like what DEC was doing with the PDP-11 chipset.
Right.
Where they created the 1103, which was essentially the PDP-11 on a chip. Which I think was probably pretty contemporary to about the same time that you guys were doing the TMS9900.
Probably so, yeah.
So you come into this, after your sabbatical, you come into this TI home computer project. You've got an 8-bit home computer that you're trying to build, and yet you have a 16-bit Minicomputer processor. This feels like a match made in hell.
Tell me about it.
So there's a lot of very quirky, weird things going on with the TI-99. And some people can like to attribute this to the downfall of the TI-99, but I think there's a lot that goes into the downfall of of the home computer, because Jack Tramiel was not a nice person and had a personal vendetta against TI. But as you're developing this TI home computer, was there you mentioned that there was a 6502, and TI brass said, no, you got to use a TI chip. Was there never a desire to say maybe expand the TMS1000 4-bit processor into the 8-bit? For reference, the TMS1000 series is why Jack Tramiel at Commodore was so upset. He was building Commodore calculators, and they were doing quite well. This is a story I've heard. If I'm wrong, you can correct me. He was building Commodore calculators, and they're doing all right. And TI came out with TMS1000, which was essentially one of the first microcontrollers out there. So it had a 4-bit CPU, a small amount of RAM, and a small amount of ROM, and it was a pure Harvard architecture. So the ROM space and the RAM space did not overlap. And you could program the ROM to do something, and the most common one was to program it to be a calculator. And so you essentially had a calculator on a chip. You had one big chip, and then you had a couple of supporting things going on. And the the 2500 data math came out and undercut anything else on the market. And so the calculator wars were in full effect, and TI just decimated anybody in their path. And Jack Tramiel got very angry and very upset about this and created Commodore Computer. And then the Commodore VIC-20 and the Commodore 64 and the TI-99 went head-to-head. And the C64 sold 15 million units, and the TI-99 sold 3 million units. So, y'all won the calculator wars, he won the computer wars.
Right.
But we're getting ahead of ourselves. So you're sitting here, you've got a TI-99, you're building this home computer, you want it to be a fast, snappy 8-bit home computer, and the 6502 is off the table. So why immediately go for the 16-bit Minicomputer? Why not work on designing your own 8-bit version of a CPU to use in this machine?
We really weren't given that option.
Oh, so the brass said it's the TMS9900 or bust.
Yeah, that's right. They just took it and forced it. Open your mouth, and we're going to stick it down your throat.
Okay. So at that point in time, did you go, well, then it would make more sense to make this a full 16-bit home computer as opposed to the weird halfway thing that ended up making it to production?
We were already pushing our price point by having the machine. The 16-bit computer costs, 5 times as much as an 8-bit computer, so to open it up anymore meant that we had a product that hobbyists would love still, but that's not the market we were after. We were after something that someone would buy in the home. So can't be priced more than a TV set.
Okay.
That's, that was kind of the price point. The price point was established that if it costs more than a TV set, people won't buy it.
Okay. So you've got this price point, you're restricted on it, and you've got this 16-bit Minicomputer CPU.
That's right.
You've got essentially the engine out of a Ferrari, and you've shoehorned it into a Toyota Echo.
That's right. I've put a little 16-bit to 8-bit converter set of chips in there, and that's what we used until we could find get relieved of requiring that we use a 16-bit processor. And eventually they were making the 9900 and have an 8-bit interface, because we built an 8-bit interface right off of it.
Yeah.
That's
so for all the peripherals and expansions and everything, it was all an 8-bit interface.
We just, because, we can't meet the price point otherwise.
Okay. And was the primary limitation on the price point the CPU or the RAM or just everything in the soup?
Yeah, everything put together, and the thing is, RAM initially to meet the price point, we were going to use 4K RAMs, but RAMs were 4 times as big almost every year.
Yeah.
And so we started with a 4K RAMs, but we put sockets in such that you could just unplug in other words, rather than soldering on the board, we went ahead and put them in sockets so that you could pull the 4Ks out and put 16s in when the price came down as they got good yields.
Okay.
And if looking at the way the technology was going, we probably needed to be even more flexible to make things grow, because every year more stuff was, the price went from here to here to here to here.
So you've got an interesting architectural challenge on your hands here, because you've got a 16-bit processor and you've got effectively an 8-bit bus for your RAM. And the way that it ended up in the TI-99 ultimately was that RAM is effectively gated by the video display processor.
Right. And
so if the CPU needs to access that RAM, it has to ask the video display processor for permission, effectively.
Right.
So what was the decision that led to putting the RAM on the other side of the video display processor, as opposed to directly multiplexing it onto the 16-bit bus that the CPU can access directly?
It's just, it was just a quick, what's the quickest thing that we can do? Because we were getting hammered by, the technology movement, that we had to move as quickly as we could. And so we just tried to take whatever we could and get it out right away. It was just like when we found that it would take a year to be able to sell a modulator to go into the TV set, because the TV companies didn't want to pay an extra $1 to have a parallel input, which they could have done, and they finally did. But that was a real awful predicament for us. We wanted to run good quality video into a TV set, and the only thing that they would have is an RF input, which is, dumb. It wouldn't cost them very much to put that other.
Dumb. And on the TI-99, you guys have straight composite video coming out, and the RF modulator is a separate box.
That's right,
that sits
exactly.
behind it, which I have gutted to go straight composite through the box to my actual TV on my TI-99.
Right, exactly.
Now, you guys had, on the initial, since we're talking about TVs, we're going to get back to the architecture here in a second, but we're on the topic of TVs. When the TI-99 released, the original one with the chiclet keyboard that did not go over very well.
No, right, exactly.
Chiclet keyboards were all the rage for all the wrong reasons. The TI-99 was bundled with a TI-99 branded, I want to say Magnavox television.
Zenith.
Correct. Zenith. That's
Yep.
what it was. Got it wrong. I'm out, guys. Sorry. And so it was bundled with a Zenith television that was branded TI-99.
Right.
So
That was just to get the product out. Otherwise,
Okay.
the problem is if you understand the marketing of that type of products, the CES show, the Consumer Electronics Show, is where 80 to 90% of all your sales take place, right there. That 1 month in January or February timeframe when it happened. And if you don't sell, 80% of all your product is going to be sold right there in that show.
okay.
And so you haven't, you just basically, if you miss the show, you cog a whole year in your product. And the competition has a whole year to try to see if they can beat you. And so what we did is said, we've got to get our product out so people see us out there. And the only thing, when we found that it was going to take a year to get the modulator to work legally, we said, what can we do? And we went and talked to the various TV companies, and the one that had the best quality was Zenith. They did 24-hour testing of 100% of all their TV sets. They had a huge building with a conveyor belt, and they dropped the TVs onto the conveyor belt, and it worked. And it went through various temperature ranges, and if it was still working when it came off the line 2 days later, it's a long conveyor belt. It was good. If it didn't, it was bad, and that's the way they did it, so that we knew that they had a high quality product. We talked to several TV manufacturers, and the GE's quality control was as long as 90% of them are good, the customer will bring it back and we'll give him an over-the-counter replacement. We said, that's just not good enough. We aren't going to do that.
So if we dial it back a bit to the architecture again, because the TI-99 architecture is quite complex, and I think a lot of this might have to do with the Minicomputer aspect of it. So the TMS9900 chip has a fully built-in hardware interrupt. So I'll try to give a quick rundown of what this means for anybody that's unfamiliar, is that a external device can send an interrupt request to the CPU, and the CPU will see this and then check a 4-bit value to see what interrupt level this is. And if it's a lower priority interrupt and something else is currently in the middle of it, it'll ignore that interrupt until the right timing happens. But if it is the highest priority interrupt that's currently being requested, it'll look at that level, jump to a specific location in code, and execute code dedicated to that interrupt level. This is something that's I personally have seen is quite common on mini computers from this era. Centurion, for example. Aaron here has a Centurion as well. So Centurion, for example, does this with everything, but notably for data terminals. So if you've got multiple users going on, each user presses a key, an interrupt request comes in, it checks the interrupt level, it jumps to that user's code. Now, this is great on the TI-990 because you guys can jump around with your workspace pointer and do all sorts of really rapid context switching for multi-users, but in the home computer, the hardware interrupt is completely not used.
Right.
Was there a particular reason why you guys decided not to use hardware interrupts? Because I think you do some form of software interrupts, correct?
Yes. I didn't spend a lot of time with our software people as to what they wanted. We gave them, we worked our part of it while they were doing their part of it.
Okay.
And they told us what they needed with the software. Now, what we were doing also with the software is that we created a intermediate language graphics programming language that was set up so that we could be independent of the specific way the hardware worked if we wanted to by just changing the drivers without changing any of the original software, so that we were doing the intermediate thing, which is the way that Bill Gates did with compilers, so that he could deliver a compiler in a month or two just by changing the targeting software. That he didn't ever have to rewrite the compiler.
So the software team is developing code purely in GPL, or
Correct.
the graphics
Programming
language, which means that if you guys change something on the hardware level, it doesn't affect the software team, so they can continue simultaneous development.
Right, that's right.
Okay. So you guys are doing all sorts of tricky things at the hardware level here. Is that particularly, since an interrupt request is an inherently software type thing, ignoring the IRQ, the hardware IRQ, was that to make software it easier for the GPL?
I didn't have to worry about that. Was between the software people and what they wanted.
Okay.
And unfortunately, the software manager, Herman Harrison, passed away a few years ago. And so we don't have him here to say why he wanted it the way he did.
Okay. So as the TMS9900 is trying to be hamstrung, but working in this thing, eventually you guys started working on expansion, because you mentioned that you had the 8-bit expansion bus coming out of the side of it.
Right.
And this is where you started doing, really exploring the speed of the machine, it feels like, because you could get the 32K expansion box for the TI-99.
Right.
That brought the total amount of DRAM up from the 16K that was built into it with an additional 32K of DRAM.
Yeah, one of the things that happened, and if you look at the box and at the expansion and the table and all that sort of stuff, that was all being pushed by a new manager in the over the program. Lynn Donahoe, who started the program, got crosswise with his manager and ended up leaving TI, and another manager came out that his idea was that computers are for people that like computers. Computers really don't belong in the home. And so we need to add to this hardware and make it so that the people that like computers will like the system. And so all that extra stuff, you aren't going to find that in everybody's living room. It's for us, not the average homeowner. And so that whole chain of product was taking a direction when he began to realize that we were really looking at a different market. But he didn't understand that when he started. He thought the computers were for him, a computer geek.
Okay. So again, we're getting a bit into the software here, but to really get the TI-99 to hum along, you would throw a 32K expansion at it, and you would run extended BASIC.
Right.
Now, there's a surprising performance difference between the built-in TI BASIC and the extended BASIC. And word on the street is this has a lot to do with the double interpreted GPL shenanigans that are going on. Do you have any insight on that?
Unfortunately, no. The software guys were charging down their street, and they were being pushed really harder than we were in hardware, because in the bottom line, the product lives or dies depending on what kind of software you can put on it.
Okay.
And we really didn't want to develop a lot of the software. We tried to make it so that anybody that wanted could develop software. We had it set up so that that we were programming it with the graphics graphics programming chips, And what that was for is to protect the software for designers. For $1,000, you could have a new, the chips were made so that the last mask said what the chip had on it. And so for $1,000, you could have your own custom chips. So anybody in his garage scares up $1,000 and he can make a custom chip that could play on our computer. And so we thought that we would see hundreds of entrepreneurs wanting to do it. Well, unfortunately, the magazines panned us heavily, saying that we were hogging all the software so that nobody could develop software, rather than making it so that everybody could develop software, and we were protecting them, because in those days people didn't know how to protect software allow software to protect itself. I mean, you could take anybody's software and pirate it and tweak it a little bit and it's gone, you know. So you have this great program and all of a sudden you see it everywhere.
So let's clarify a bit, because the GROMs, or the graphic ROM chips,
Yes.
that we're talking about here, is kind of a unique thing to TI.
Yes.
None of the other home computers had anything similar to this, and I don't even think that the TI-990 had anything similar to this, the Minicomputer.
No.
So what, from a hardware perspective, what are the GROMs, and how do they interact with the TMS9900?
Well, to start with, the GROM used, we wanted to make them, they're very competitive cost-wise, so it used P-channel ROM chips.
Okay.
And the P-channel is what, like a fourth of the cost? You can say better maybe than me.
Well, no, it's cheaper. We made the P-channel, probably P-channel metal gate, the same thing they make calculators in.
Right. And so we knew that we could make them cost really low, and so anybody could order and have his own mask and make it easy. And so it was using the P-channel technology, because you didn't need blinding speed.
Yeah.
I mean, you couldn't be too slow, but it was plenty fast enough with the P-channel devices, and the P-channel is less expensive, and so you could have solid-state software for any designer that wanted to make his own software stuff.
So the GROMs contained what? What was contained in the GROMs?
Basically, it had the chips, and it had the byte-wide bus coming out of it, and that interface is basically the same type of interface you have in all of your memory sticks that you use today. It's that interface is covered by a currently expired my patent for the interface to put it into the memory.
Okay. So what software was on? Like, what did they contained the interpreter? They contained the GPL interpreter.
No, they contain whatever you programmed in it, but the interface was just we wanted the chips to be minimum expense, so we put them into a standard DIP package. We didn't want a 16-pin or bigger package. We wanted it to fall into a, let's see, was it?
I think they're 14-pin or 16-pin.
Yeah.
I don't remember.
It's in a package that is super high volume with a minimum dip cost. So it had the same package that all the TTL dips are in, which is the cheapest package, highest volume package in the world. And so we put it in that package, and with a interface, and then inside the machine, it just is just memory. It's just a memory chip.
Yeah, which is
With no smarts inside there.
But because you put it in such a small package, you can't feed it a memory address directly, correct?
Well, you have to feed it. In fact, that's the way the interface works, is that you feed it a byte at a time.
Okay.
So you have the first byte, second byte, third byte if you need to have a bigger, as the chips grow, the specification allows you to, so that same methodology is what you use in your memory sticks because they don't have enough pins to address a bunch of memory. You just keep sending it bytes, and then when you quit sending it data, you read whatever that data pointed at.
Okay.
So you do address, 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 data out. Address, 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 data out.
Okay.
So that methodology is what we had designed the chips to do.
And then that data out that's coming out, particularly for the GROM chips that are built into the TI-99 motherboard, contain the TI basic software. Like when you turn it on and you get to the ready prompt, that ready prompt is being displayed and TI basic is running out of the GROM chips.
Right.
Okay. So that's your core software that's built into the machine.
That's right.
Okay. Now the last thing that I want to grill you about, because I'm trying to make a homebrew out of this, and I'm like, GROMs, those are out. I'm not using those. There's one more aspect of the TMS9900 that I looked at and I was like, no thank you. And that is the CRU. The CRU is a pretty weird aspect of the TMS9900. For most other mini computers that I'd come across, they do peripheral interface using MMIO, or memory mapped input output. So they use a memory address and there's a peripheral that's listening to that memory address, and then it either reads a byte or supplies a byte. But TI didn't do that with the 990, and they didn't do that with the TMS9900. You use something called the CRU. So what's the CRU?
It's the part of the interface. I let the software guys worry about that. I didn't worry about it.
So from a hardware perspective, what is this? What is the CRU? Or this is how good it is. He was like, I don't know, no thank you. So as I understand it, it's like a dedicated 1-bit bus specifically for peripherals.
Right. Yeah, and we didn't have to use it.
Bus. You had to put up a whole address bus, which only got 1 bit. So it was like you were sending a huge amount of address bits, but 1 bit of data each direction.
Why?
That's the way they defined it.
Oh, we got him over there. All right, this is now a group effort.
So, if you read Ed Millis' biography, there's a great deal in there about why it makes sense. Ed Millis, his biography is TI, the Transistor and Me, My Disintegrated Journey Through Texas Instruments. Ed Millis was in semiconductor on test equipment and employed Mike Bunyard over there, also from later Home Computer. But when they got the 960 and the 980, they were overjoyed because it had 1-bit input and outputs. And that's what they needed the most for factory control. You set things, single switches on and off for all sorts of reasons. And TI also had a part, the 259, the TTL LS259, which was an addressable 8-bit latch. You could set any of the 8 bits in the latch. And the 9900 has an instruction for setting 1 to 16 bits of a latch all in one instruction. So you could set a portion of the register. And the CRU was ideal for that sort of 1-bit, 3-bit field, 15-bit field I/O, so that they all changed at once. And the semiconductor test guys loved that. Obviously,
CPU is as complex as a multiply. It's basically like doing a multiply instruction. So it was one of the most complex instructions in the CPU because you had to take that in, and then you did all this machination to run out. You run all these addresses out, all this other stuff out just to get 1 bit of data going anywhere. So it's a lot of work on the CPU to move 1 bit of data around.
It was good for a flight control computer.
Yeah. I mean,
It was perfect for that.
It made sense for something else, but it was a lousy way to do computers.
Yeah, we didn't use it for the home computer.
And they were bandying the term, they called it the bit pusher. And
Okay.
there's a color advertisement that I found in, I think, Mini Microsystems or Electronics Magazine, where they go all in on that phrase. They say, the bit pusher, and it's advertising the 960.
So now that you mention automation, that does make a massive amount of sense because if you're feeding it a relatively large address, you can turn a whole lot of peripherals on or off. But if you need to retrieve a byte from something,
Serial port.
yeah, now it's tough, right? Okay, so
You had to put out things like the 9901 and the other chips. You ended up having these other chips that talk to it.
there's
Turn it into something that anybody could use.
the CR even within this is the block diagram for the our printer is dying. This is the block diagram for the TI-99, and the CRU portion of it has all of this extra control logic and stuff going on, and I was really perplexed by it because, like as you said, it's an incredibly complex collection of instructions, which is going to take up a huge amount of transistors on the die. So this is something that they're like.
For us, it was a lot of microcode. I know that. It was like I say, more complicated than a multiply. It was like the most complicated instruction on the whole chip.
So you dedicated a massive amount of transistors to this.
Yeah, I don't remember
And
a
it
lot
was-
of transistors. I do remember a lot of I mean, it was a complicated instruction
Okay.
relative to this day, anyway.
and I feel kind of bad because it's like I just looked at it and was like,
I don't think anybody who dealt with it liked crew. If you put crew out, you talk to we were some TIers, we talked crew, and you say the word crew, and everyone goes.
All right, well, I'm glad I'm not alone in that. I felt kind of bad for a little bit. Yes, sir.
Would you feel better if it was a SPI interface or a I2C interface?
I like parallel interfaces.
Well, it still has parallel interface. The memory I/O still works.
Yeah.
Okay, they just don't advertise it as such. You you just dedicate its memory space and call it.
Yeah. So, but I mean, I suppose you could say it because when I think of serial, I think of RS-232 serial.
Yeah.
Which is more like you have a dedicated UART that is doing the serial to parallel translation for you.
A lot of controller chips have an I2C or
SPI.
SPI interface.
Yeah.
And this is sort of a predecessor of that concept.
Okay. Yes, sir.
Just wasn't adopted by anybody else.
The problem is that you're tying up the whole CPU. The CPU is going clock, 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 clock. You ship out bits.
Yeah.
What you really wanted to do is dump it into a register and have it.
Which is
shoot out
why.
serially, like an RS-232.
Yeah, which is why I like the RS-232 thing.
Right. That's what you wanted, but that's not what we had. We had this crew thing, and for compatibility reasons, I had to design it twice. So
Because my plan is the UART receives a byte and just throws out an interrupt. Hits the IRQ port and throws out an interrupt level, and then the CPU, when it's ready, grabs that byte from the bus, which is, I feel like, the pretty standard way to do it.
I think most people, most other things, yeah, they just throw it in some shift register or something, or
Yeah.
the thing and go. But you shut down the CPU. The CPU is going ka-chunka. Every bit's that's got to go out. You got to ka-chunka, another cycle, another cycle, another cycle. You tied up the whole CPU while you're just trying to send a little bit of bits out. So whoever was doing it wasn't worried about tying up the CPU when they did it.
Well, I suppose this goes back to what you were saying, is that if it was about automation, that's the top priority, is turning.
Yeah, that was probably the
Let's
job.
have a CRU panel next year.
Okay. I don't want to be part of that one.
Fight it out.
Take it out.
Just one bit at a time.
Yeah, one bit at a time. I will say I am immensely relieved to know that I wasn't the only person that looked at this and went, I don't want to use that. We're coming to close on our hour here. These guys have chimed in, but it seems like we have a ton of really smart TI people in here. Does anybody have any questions for this group of brilliant minds? I'm excluding myself from that group.
Why didn't they make the registers in the memory instead of just store the registers locally?
It's an excellent question. Why are the registers in RAM instead of on the CPU itself?
That was a concept that came out of a flight control computer that they had designed for the F-16 and the F-22, and
Okay.
so they thought that they would put the registers all in RAM, which is not bad, except it saves a lot of the register hardware, particularly if you need to have hardened hardware for military fighter aircraft. And so that's where that architecture came from, and what they made it good for.
I think for the 990, it almost made sense because it was trying to be early. TI decided we were behind in 8-bit, although they did an 8-bit copy of the 8080 that was bigger and slower than the Intel's. But they did before my time, so that's why I said so. But it was cheap. It was locally optimum cheap. It was a cheap way to do a 16-bit processor when the 9900 came out. But within a couple of years, it became the, like I say, bane of my existence, because it took all the other guys doing CPUs were doing one cycle to do an add, or one operation. We had to do 4 memory cycles to do an add. Read, write, 2 reads and a write plus an instruction. So it was optimum maybe early on. The context switch, I think you can argue, was always a bogus argument. Because if you look at how many memory cycles you have to do, if you do a short context switch, well then you'd only move a few parameters, and so you don't really need to save much. And if you did a long context switch, a few instructions in, I think somebody said 2.5, 3 instructions in, you've already broke even on memory accesses, and now you're in the deficit. But I think it might have been one of those things that made kind of sense when the 9900 was done, but within a couple of years, you could integrate that RAM on chip, and you could integrate the register file on chip, and then you go 4 times faster.
Yeah, just be pick up later.
So.
Did the original TI-9, we're going to get to you in a second, the original TI-90s, did they use core memory? Or yeah, so the early Minicomputer that was building this architecture.
Core memory, yeah, sure.
They were using core memory. The
980 used core memory.
They used core memory, okay.
Would the 990 have had core by then?
Yeah, no, it was still core memory, I think.
990 was.
Because you had these relatively expensive 1K chips is all you could get for solid state memory at that time. And so at the time that all that stuff merged in Austin, the memory chips, even the 4K chip wasn't available. And so those processors didn't have that as something they could use. So they were using core memory, and then it went to solid state memory within a couple more years.
You had a question, sir?
Yeah, so I'm curious as to how many sets of these workspace registers you could have in memory, so that if you were running some form of an OS that could multitask, how many task sets can you have to do switching?
At least 32. I think you could do, it depended on how much memory you got. I mean, you can, and I don't recall if there was a boundary. That's in the bailiwick of our software guys, which I didn't know. It was way more than we would ever have to worry about, but I think it would have at least 32.
Yeah, you had a workspace pointer, which is 16 bits, and I think it's shifted. I forgot now, but I think they shifted it over. So, yeah, basically, you could have gone to a lot of memory with that.
If you got enough memory for them, you could just have work coming out the kazoo.
You had a question, sir? Oh, all right. We answered it. Yes, sir.
So if they would have let you use a third-party processor, do you think the line would have lasted longer than it did?
Yeah, I think we could have for sure been competitive. The reason that we quit making the home computer was because the manager that came down from DEC lowered the price to $100 and the cost was $127. And you say, well, that's bad to be shipping $27 out of the door for every machine you sell, but we could have even survived that. Selling below cost is blatantly illegal. So within a few weeks, it was either TI goes out of business or they get rid of all computer business. I mean, it's just that we would have suffered like companies have a problem, and if by saying, hey, the problem is with the computer group, and if we get rid of all computers, we're okay. Otherwise, they'll put TI out of business. You can't sell below cost in a competitive market. That's illegal. The railroads used to do it, and they passed the Anti-Sherman Act, the Sherman Antitrust Act, which was to cut up the railroads and cut up any business that tries to put their competitors out of business by selling below cost. So you're forbidden by national law to not sell below cost in a competitive market.
So I think we have time for one more question. Sure.
So you mentioned that the target cost for the computer was determined by the price of TV at that time. And how much was the cost at that point?
TVs at that time were going for between $250 and $500. A real inexpensive cheap TV would go for about $250, but a good TV would be about $500.
And did y'all meet that price point?
Well, we were selling at $150, so our price point. We weren't making much money, and we needed to do some cost reduction to be making model profit. But we were making a profit at $150, so we didn't. It was until he dropped the price. Our cost was $127, and we were selling at $150 because that's where the market was going. But we had a lot more to offer than the other people. But you still are in a price competitive market.
What was the cost of the Zenith, the original monitor, the TI-99?
I think we had to sell it at $400. I think that's about what we. It was just their basic TV modified so that that you had the input into it.
Yeah.
You bypass.
It's actually brilliant. It's a really nice. You have a 99.4 branded one? Yes. You won't for long. I've been searching for one. All right, last one.
Dr. Ott, can you speak to competition between the home computer project and say the professional computer or other computer projects at TI? Internal competition?
No, we were all, we were essentially totally independent. We were in the consumer division where the calculators and then later the speak and spell and all that stuff was coming out of them. So that's totally independent of the other product divisions. So there wasn't any competition. Other than occasionally we were forced to use product that may come out of other divisions, but other than the semiconductor stuff that we had to use, none of the other divisions had stuff that was forced down our throat.
Well, Dr. Ott, I want to thank you so much for allowing me to pick your brain here. I hope I didn't make too much of a fool of myself with my limited knowledge of the system, but there are a lot of smart people involved in this TI TMS9900 collection, and I'm going to use this knowledge to hopefully build my own homebrew computer that I hope to bring here next year. So hopefully I can get it here running some interesting code.
Well, I'll be looking forward to that. And if there's some questions, I'm not going to swear that I can answer any of them, but I'm in Austin, and I'll be happy to let you have my email.
Well, if you didn't give it to me, I would still steal it from Jay over there, so you're going to have to answer those questions anyways. All right, well, I think that wraps us up. Thank you guys so much for joining. Big round of applause for Dr. Ott.